In section 1.4, we will be finding definite integrals by using trapezoids and using algebraic equations and data, both equations and data in order to do this. So what we're going to be looking at is a second method to find the area under a curve. That's our definite integral from point A to point B. And instead of counting squares to find our integral, we are going to divide this segment into equal parts, say 6 divisions to start. And as we draw each division, we will find the area of each one individually by finding the area of a trapezoid. When we add all of the trapezoids together, we will get an approximate value for the definite integral. Oops. And the last trapezoid here. As you can see, this is a fairly close approximation of the area under the curve by adding up all of these individual trapezoids. If you look in your textbook at example 1 on page 18, or excuse me, the introduction on page 18, you see that they show you how to calculate the area of a trapezoid. Remember, the trapezoid is 1/2 the height times B1 plus B2. In our illustration, since our trapezoids are laid up on end rather than in this configuration, our height is actually our distance on the x-axis, our subdivisions, and our base sub 1 and base sub 2 are the y values at each individual subdivision length. So we're going to start with a value at x equals, for example, 1. And if we have divided this into equal segments, 3, 4, 5, 6, 7, then our base lengths would be f sub 1, f sub 2, f of 3, f of 4, etc. So to find the area of the first trapezoid, I would take 1/2 of this distance, which in this case is 1, times f of 1 plus f of 2. And then I would add that to the next division, again 1/2 of this distance, which corresponds to our height, times f of 2 plus f of 3, etc., until I get my areas. This is translated into the trapezoid rule. I'd ask you to take a minute and copy this down. It is the definite integral of f of x from x equals a to x equals b. And again, that's our general definite integral when we are taking the area under a curve from a to b of some function f of x, is approximately equal to the total of n trapezoids, however many divisions you use, where we take the change of x times 1/2 of f of a plus f of x sub 1, f of x sub 2, etc., until we get to 1/2 of f of b. Now this is a little different than the formula that I gave you a moment ago, and I'll show you how this works in just a second. N represents the number of increments. How many divisions do I make in my areas? Delta x is the distance from A to B divided by, or n, or in other words, the width of each increment. And x sub 1, x sub 2, x sub 3 are spaced delta x units apart. Let's look at this for a moment with our original explanation. If this is A and this is B, and we divide this into n divisions, then each division will be A minus B, or excuse me, B minus A divided by n. and that's going to be my delta x, which we said before, if we take one of these trapezoids and lay it the way we're used to seeing a trapezoid, that delta x is the same as our h. Our values here and here would be f of a and f of x sub 1, if this is our first division. Now what they've done is they've consolidated this formula. If I wrote it the way I did a minute ago, I would have 1/2 of our delta x times my first division plus my second. Then I would do the same thing. You can see that I'm repeating the 1/2 and the delta x each time. So to consolidate this, they have written delta x times half of my first y value plus half of my second y value, but you can see that I'm going to use this twice. I'm going to use f of x sub 1 at the end of the first trapezoid, but it's also going to be the beginning of my second. So instead of having to say 1/2 plus 1/2, I can just use that second value. And I continue with all the intermediate values repeating twice until I get to the end where this last value, f of b, is only used once, so therefore by the formula times 1/2. And that's how they get the trapezoid rule. If you would please take a moment and look at example 1 in the textbook. This example is from data. In other words, they have given you a table, looking at example 1, where the x values are evenly spaced, 0.1, 0.2, 0.3, etc. And the f of x values are given 11, 28, 32. Excuse me, I'm sorry, the first one was 22. They've already done the half at the table below. So looking up at the top and using example 1, they have taken their trap rule and worked through to get 0.3. They're using every third division times 1/2 of 22 plus 34, which is the next value they're using since their delta x is 0.3, etc., until they get to the last unit, which is 0.1. Please take a moment and look through example 1 in your text. So we've written the trapezoid rule found on page 20, and here is a definition for our definite integral using the trapezoid rule. The exact value of the definite integral equals the limit of the trapezoidal rule sum, t sub n, as n approaches infinity, provided the limit exists. I'll explain this in just a moment. The exact value can be estimated numerically by taking the trapezoidal sums with more and more increments and seeing whether or not the sums approach a particular number. Please write this definition in your notes. You can pause at the moment and take a moment to do that. So what they're saying here is that if I have a particular curve under which I want to find the area from point A to point B, and I use trapezoid sums in order to accomplish that, obviously the larger my increments, or in other words, the fewer number of divisions, the less accurate my estimate will be. So if I take the limit of these trapezoidal sums, if you remember limits from pre-calculus, it means what happens as we get closer and closer. We're taking the limit of the trapezoidal sums as n, which is the number of intervals or divisions, approaches infinity. In other words, if I take more and more subdivisions, if I make these segments smaller and smaller, as the number of divisions approaches infinity, you can see that the error at the top of each trapezoid becomes smaller and smaller. Therefore, if we take the limit of the trapezoidal sums as n approaches infinity, we can get an exact value for the definite integral. So this last step is to combine that idea of taking trapezoidal areas and then making those intervals smaller and smaller, making more and more subdivisions until we approach a very, very accurate estimate of the definite integral, which again is the area under the curve. So as you're working on your homework, please keep in mind two things. One, we need to use the trapezoidal rule for this entire section. Again, we are doing the Q questions before you begin, and then we're going to be doing the odd problems. Now, number 5 asks you to put a program into your calculator which will allow you to do subintervals of a greater number. In other words, when you have 50 or 60 divisions. This is very hard to do manually. We will do this in Jumpstart. So don't worry about number 5. And then in 7 through 11, if they ask you to do more than 10 intervals, more than 10 subdivisions, please wait for Jumpstart to do that. You can do the 4 or 5 or 6 divisions, anything up to 10 divisions manually, but wait for Jumpstart to do anything greater than that. Also, please look at section 1-5 where they ask you to begin a journal. This, I think, is a very, very important tool to use throughout the year. I would like everyone to begin a journal, whether it's a separate small notebook or a set of index cards, or maybe one of those index cards that's on a ring binder so that you can keep them all together. And look back over chapter 1 and write down some of our key definitions, some of our key formulas like the trapezoid rule, and some of the key concepts. One concept or formula on each note card. I'm going to ask you to keep these journals throughout the year as a tool that we can then use as we approach our work for our AP exam. So, good luck with section 1.4, the trap rule, and I look forward to seeing you all at Jumpstart. Please bring all of your work with you. Please bring your notebooks with you. Please bring your books with you, and we'll see you at the beginning of the year. If you have any questions, please email me, and we can communicate over the summer. And or email some of your fellow students, and feel free to get together on the phone or in person to work through some of this work together. Best of luck, and we'll see you soon.